Hey guys, Mr. B here. In this video, we're going to be going over chapter 5.3 on quantum mechanics and physics and how light works. Okay, so this chapter section is going to have a lot of vocabulary in it and a lot of very heavy physics words. So we'll do our best to try to explain them to make sure we understand what they are. Okay, but we're primarily going to be talking about light and how electrons work. All right, so let's talk about light. Okay, now light is something that you are familiar with, of course, because every single day you see light bulbs and you see the sun, and there's light. You can see things if there's light, and you can't see things if there's no light. But you maybe aren't quite as familiar with light and what it is. You probably think of light as only visible light, right? Which is you turn the light on and I can see stuff. But that's just one type of light. Okay, and not only that. There's all kinds of different types of light that you can't see, and what is light exactly. So first, let's understand that light is a wave. Okay, a wave. What do you mean by that? Exactly as it sounds. It's a wave, like a wave would be on a lake, right? If you throw a rock in a pond and it ripples, that's a wave. Light is a wave. Okay, it moves like a wave does. And so when we talk about light, there are a lot of different properties about it that behave like waves do, and that gives us information about how light is going to interact with other things. So first, we're going to learn some vocab here, okay? And there's going to be an image, and I'll show you what these things are. So we have amplitude. Amplitude is the height of the wave, okay? So some waves are very tall, and some waves are very short, right? Think of like a giant tsunami. You have a giant wave of water that's going to come and crash into buildings and destroy things versus you throw a rock in a pond, you have little waves that are not very tall and they're going to be just fine. You have wavelength. Wavelength is going to be the distance between waves. So if you have, let's say you throw a rock in a pond and you have, ripples, the waves are going to be, not that far away from each other, but you'll have a bunch of waves that are kind of close to each other. Versus if you have like something really big and you throw it in the water, it might make a big wave, and then another wave is going to come later, but they're further apart from each other, right? So it has a longer wavelength, or the distance between waves. You have frequency, which is how many waves come by every second. So high frequency means that there are lots of waves that are all coming by. So it's like, like this, like up and down, up and down. You have all these waves that are like coming by really quickly, versus a low frequency means you have one wave, and then another wave comes by later, and then another comes by later. Okay, that's lower frequency. We measure frequency in cycles per second, which the SI unit for that is hertz. Radio stations, like when you listen to the radio and you turn your little dial and you tune it in to whatever, that is measured in hertz as well. We abbreviate that with an HZ, okay? So this image here kind of shows you all of these different vocabulary words. So amplitude is the height of the wave, again, from the middle to the top or the bottom, or the crest is what we call it. We have wavelength, which is the length between waves. We have then frequency, which is how often a wave is coming by. So low frequency, which is this red one, shows there's like 2 waves here. Versus high frequency, we have, 1, 2, 3, 4, 5, 6 waves coming by. Not to mention, too, they have lower wavelength. So wavelength and frequency are inversely proportional, meaning if you have a large wavelength, right, or a long wavelength, you have a low frequency. If you have a short wavelength, you have a large frequency. Okay, so they're inverse. So if one is large, the other is small. Or if one is small, the other is large. Okay. So we have an equation here that is going to be very useful later on. And this equation is how we can calculate the speed of light, which is a constant number. The speed of light is going to be... I'll write this in here. It's not written. I don't know why that just made a copyright. But anyway, let's put that back. So, stop. Why are you doing that? Okay, I don't know how to fix that. Can we... What? All right. Anyway, whatever. I don't care anymore. So the speed of light is a constant number. It is 3.0 times 10 to the 8th meters per second. So that basically is how fast light travels. It travels like 3 billion meters per second, roughly. Okay, or so. It's really fast, obviously. And to calculate this, we're going to take the wavelength of light, which is represented by this weird looking H symbol. It's known as lambda. It's a Greek letter. Multiplied by this symbol, which looks like a V. It's the Greek letter nu, which represents frequency. Okay. I believe it is, maybe it's not given. Okay, I thought it was given on these next slides. So we're gonna write it out here, but how do I type? There we go. All right, so C is the speed of light. Let's go insert and special character. Let's just type in lambda. So there's lambda. And then, so this is equal to wavelength. And wavelength is typically going to be given in the units of meters, okay? It also can be given in the units of nanometers, which is very common, but we're going to keep it as meters. And then again, we have this other Greek letter, which is nu, okay? And this is spelled N-U, nu, like a new car, but just N-U, not N-E-W. I guess it doesn't really matter. Let's just do this. Let's do this one, I suppose. This is the Greek letter nu, and this represents frequency, which is given in hertz. Okay, so lambda is the letter, that's the Greek letter, and this is Greek letter nu. So if we take the wavelength of any light multiplied by its frequency, we will get the speed of light, which is a constant number, and you can Google this number, but it's 3.0 times 10 to the 8th meters per second. Again, this is an equation we're going to use later on, okay? Okay, anyway, continuing on. So, according to the wave model, which is basically that light is a wave, it is actually electromagnetic radiation. So, the one thing about light that you probably aren't aware of is that it is radiation. And maybe when you hear the word radiation, you think of, bad stuff, right? Usually things that give off radiation are not good for you. They can make you sick. They can give you cancer. They're used sometimes to treat cancer patients, right? Chemotherapy. That is light. All forms of light are radiation. Now, not all forms of light, however, are bad for you. Okay, there are certain types of radiation or light waves that will damage your body and give you cancer or make you sick. And there are other forms of light waves that are radiation that are very weak and basically have no effect on your body at all. So radio waves, microwaves, infrared waves, visible light, all are different types of light waves. Of course, our eyes can only see visible light. We can't see infrared waves or microwaves or radio waves, but we know that they're there because we have equipment that can see those things, right? We have night vision goggles that can see infrared, heat vision goggles that can see infrared, and other things like that. But those waves are very weak because they don't hurt us, right? We have radio waves literally flying through the air all the time. If you have a Wi-Fi, or if you have Wi-Fi in your house or a wireless router, there's radio waves like traveling all throughout your house right now. They don't harm you. Okay. Not to mention, of course, we have cell phone towers, which constantly are sending radio waves to your cell phone so that you can make phone calls and text messages. Doesn't have any impact on your body. Okay. They're very weak. They can't even penetrate your skin. Ultraviolet waves, X-rays and gamma rays, on the other hand, which are more higher energy versions of light waves, can damage your body and they can make you sick. Right? Enough ultraviolet waves, or UV, which comes from the sun, can give you skin cancer and other things. X-rays, of course, can do damage internally to you. That's why when you go get an X-ray at the doctor's office, they oftentimes have you wear a lead bib or some kind of thing to cover your internal organs, because they will damage your internal organs because they can go through your body, and lead can block them. Gamma rays, which probably none of you have maybe ever dealt with gamma rays. Very dangerous and typically come from like outer space and stars and stuff, but can be very, very damaging and can, again, make you very sick. Okay, so all of this is types of radiation, and all of these are forms of light. It's just that we can't see them with our eyes. Okay, visible light is the only light we can see with our eyes, so that's probably the only light you've ever thought about before. Anyway, so all electromagnetic waves, or light waves, travel at a speed of 2.998 times 10 to the 8th meters per second. This is the speed of light. I just rounded it up in the previous one. This is just a more specific number. It's basically the same thing, but anyway. So sunlight itself consists of light with a lot of different wavelengths and frequencies. And when sunlight passes through a prism, it will break apart into all these different colors, which we call a spectrum, right? Or maybe what you call a rainbow. The spectrum, or the visible spectrum, are all of the forms of light that we can see with our eyes, which again is red, orange, yellow, green, blue, indigo, and violet, with red light being the longest wavelength and the lowest frequency. So this is what we call the electromagnetic spectrum. And down here at the bottom shows all of the different types of light waves that exist. It shows their wavelength down at the bottom, which is in, again, meters. And up at the top, it shows frequency, which is given in hertz, or basically inverse seconds. And this tiny little portion right here, which they have actually blown up to make bigger, this is the visible light range. So of all the different types of light that exist, there is one little section of light that you can see with your eyes, which is visible light. Otherwise, all these other types of light you can't see with your eyes. You'd have to use special equipment or some kind of tool to see those light waves. Okay, which we have telescopes and stuff that can do that and take pictures of stars. They usually do so not in visible light. They do it in like infrared and ultraviolet light and gamma rays and X-rays and stuff. So, but lowest energy is going to be the red color. Highest energy is blue. Okay, so high energy light waves are blue in color, low energy are red, and then all the ones in the middle. You'll notice here they're also giving the wavelength in nm, which is nanometers, not regular meters. That's also commonly done, but whenever you want to use it in equation, we have to have it in regular meters. So, all right, so here's a problem. It says calculate the wavelength of the yellow light emitted by the sodium lamp shown if the frequency of the radiation is 5.10 times 10 to the 14th hertz. And it gives it to us in inverse seconds, which is fine. So, all right, so let's delete this picture. Let's insert a text box so we can do some typing. Change our font size here and our font color. All right, so we have an equation again, which is C. So the speed of light is equal to lambda. So we're going to go insert lambda times nu. Okay, so this is our equation, and they are giving us frequency, which is 5.10 times 10 to the 14th. They want us to find wavelength. So if we rearrange this equation, we will get that lambda. So insert lambda, because that is wavelength. We'll get that lambda is equal to the speed of light divided by frequency. Now, the speed of light, again, is a constant number. It was given to us actually on this slide right here. So 2.998 times 10 to the 8th meters per second. So we're just going to copy paste this. So we're going to have lambda, or wavelength, is equal to the speed of light, which is this number here. And let's, again, change our font size and our font color and underline it. Put this in parentheses. Okay, so wavelength is equal to speed of light. Man, I can't type tonight. There we go. Divided by frequency, and the frequency is given to us right here. So it's 5.10 times 10 to the 14th cycles per second. I'm just going to write it as per second instead of hertz, but either way. So all we have to do is just divide these two numbers, and we'll get an answer. Okay, it's super, just a basic algebra problem. So I'm just going to do this on my cell phone. So 2.998 times 10 to the 8th, and divide this by 5.10 times 10 to the 14th equals, and we're going to get a really tiny number, okay, because light waves are not very big. So we'll get lambda, just copy paste this, is equal to 0.000000, and I guess let's go to 3 significant figures, since our frequency has 3 significant figures. The speed of light constant doesn't have significant figures because it's a constant. Constant numbers don't have sig figs. So 5878. This is going to be in meters. But if you want to put it in scientific notation, it would be 5.878 times 10 to the, and let's see, we have to move it over 1, 2, 3, 4, 5, 6, 7 places to the right. So it's going to be -7 meters. Oh, meters. There we go. Okay, so this is our wavelength emitted by that yellow light of sodium vapor in that lamp. Okay. Moving on. So let's talk about atomic spectra. So what causes atomic emission spectra? So first off, what is atomic emission spectra? Basically, atomic emission spectra is where you take an element and you burn it, and you then take the light and you put it through a prism and you break it apart into all the different colors that it makes up. And a lot of times you're going to get these black lines, or these colored lines that will appear that tell you what the element is made out of, okay? And these black lines are like a fingerprint for specific elements. So every element will have a very specific atomic spectra, which can be used to identify what it is. So when atoms absorb energy, what happens is the electrons will jump to a higher energy level. We learned about energy levels in the previous section. But they don't want to keep that energy forever, so what they'll do is they'll get rid of that energy. They will drop down to a lower energy level, and when they do that, the energy that they give off is usually emitted in the form of light. And then these little bands that appear are the amounts of energy that they're giving off, and they're different colors, okay? We did a flame test lab in this class already, and we saw these different colors from all these different elements. And again, I tried to explain during at the time, they burn different colors because they have electrons in different places and they absorb different amounts of energy. They give off different colors, okay? So that's basically the gist of it. But this can be very helpful, again, in identifying different elements in different materials, as well as we oftentimes will use this in astronomy because stars, of course, are made out of all kinds of elements, and we can take the light that stars give off, we can break it apart using a prism, and then we can also use that to determine what elements are found inside of stars. This is how we know that stars are primarily made out of hydrogen and helium, as well as other elements like nitrogen and oxygen and sulfur and sodium and stuff like that. Okay, so as we break apart their light and we look at their atomic spectra. So the frequency of light emitted by an element is going to be broken up into discrete lines, again called an atomic emission spectrum. And if you burn these things or you energize them with either electricity or fire, they're going to give off different colors. So these two pictures here show mercury and nitrogen gas inside of a little glass tube, and you run an electric current through it, and then the tube glows a different color, or it glows a certain color. If you were to put this in fire, it would also burn that color as well. So, all right, so an explanation of atomic spectra. So how are the frequencies of light an atom emits related to the changes of electron energies? So in the Bohr model, which was back in the first part of this chapter, he talked about how electrons have, again, a specific amount of energy that they need to absorb to jump to the next energy level. The lowest possible energy that they have is what we call their ground state. And you can excite the electrons by giving them energy either through heat or electricity or sunlight or some kind of energy form. And you can excite the electron to absorb energy, jump to an excited state or a higher energy, and then when it drops back down to its ground state, it will release that specific amount of energy, again known as a quantum, and then the amount of energy it gives off will then pertain to a particular color of light. And so this is how we can determine what elements are made out of what, as well as we can also figure out how much energy these electrons are absorbing by looking at the frequency of the light that is given off, the wavelength, the color, and all this stuff, and that then can give us information. Okay, so for hydrogen, for example, when we excite hydrogen or we burn it or energize it, it will give off specific lines in its spectrum. Some of these, of course, are visible to our eyes, so we can see these. Others, we have to use a spectrometer or some kind of machine that can show us this because we can't see it. And each of these lines that we see on the spectra pertain to electrons jumping and falling from different energy levels in different places. So the first one we have is the Lyman series, which is going to be an ultraviolet. So you could not see this with your eyes. And these are when we have high electrons in energy levels, 7, 6, 5, 4, 3, 2, and they're all falling down to the ground state, which is level 1. Then we have the Balmer series, which is where we have all these electrons that are in higher energy levels, but they're all falling down to energy level 2. Then we have the Paschkin series, which is in infrared, and all of these are electrons, again, at higher energy levels that are all falling back down to energy level 3. And so each of these gives off a different amount of energy when it falls, and it will then show a different absorption line on the spectra that we then can see with a machine, and this would identify that it is hydrogen. All right. So the last thing here to talk about is just quantum mechanics and how is it different from regular classical mechanics or regular physics, basically. So in 1905, Albert Einstein, which of course all of you probably know, he's the most famous scientist that we have for the most part. Basically, he's explained that light itself can be described as a quanta of energy, meaning that it is very specific. Quanta means it's specific. There's a specific amount, a specific quantity, okay, of energy. And that these quanta of energy behave as particles, and he called them photons. So there are particles of light that we call photons, and they behave like particles. But then in 1924, there was another scientist, the last name of de Broglie, who developed an equation that predicted that light actually has a wave-like behavior. So it's not actually a particle, it's actually a wave, like you'd find on the ocean or in a lake or something like that, which of course was very strange at the time because it's like, well, how can you have particles and also have them act like waves? Like, that doesn't make any sense, right? It's either a particle or it's a wave. It can't be both, right? That'd be like having a tennis ball, and then also the tennis ball is a wave on a lake. It's like, it doesn't make any sense, but that is how light works. It's a very weird concept, and there's a lot of weird physics that at the level we live at, you don't see things happen this way. But at the very small scale, like atoms and light waves, things don't work the same way that we think they do on large scale. Okay, so these wave-like properties that light has been very useful because it's allowed us to make microscopes, such as the electron microscope, which can basically use electrons that are smaller wavelengths than visible light, and you can get really, really enlarged, clear pictures of very, very small things, such as this dust mite, right? You could not see this with a regular microscope, like with glass. It's too small. So it has been very useful, but anyway. So classical mechanics basically describes the motion of bodies like larger than atoms. So big things, what we call macro things, like, cars and humans and large objects. Whereas quantum mechanics describes the motion of very, very small things like atoms and protons and electrons, and the very, very small universe does not work the same way as the universe that we live in on a regular basis. Again, you're used to seeing cars moving and all this stuff, and atoms don't work that way. Electrons don't work that way. It's a very strange world that they live in, but you'll never be able to experience it because we're not that small. So there's a principle here called the Heisenberg-Uncertainty Principle. This was brought up a little bit in the second section of the chapter. And this basically just is the whole reason why quantum mechanics is so strange. It basically says that you can never know exactly where an electron is ever found inside of an atom, because the act of actually trying to observe it will change its velocity and change its position, and therefore you can't image it. So this limitation obviously doesn't matter with large size objects. For example, if I wanted to take a picture of a car, I could take a picture of a car and the car is sitting right there. But if I wanted to take a picture of an electron, I'd have to shoot a beam of light or some kind of particle at the electron. It would have to bounce off the electron back to my sensor. Then I could get an image of where the electron was, but the act of doing that actually moves the electron to a different location. So I can't ever actually know where an electron is. I can only ever know where it is usually found. This was talked about in the quantum mechanical model, again in the second section of the chapter. This is why the quantum mechanical model predicts the probability of where you find electrons, but there's no way of actually knowing exactly where an electron is found, because the Heisenberg uncertainty principle basically says just trying to view an electron will move it somewhere else. Okay, this will come up. This really won't come up actually much more after this, but this has a little bit to do with chemical bonding and stuff, which will be in the second half of this course in quarter 2. So, all right. Anyway, so that is it for this section of notes. I know that was probably a lot of physics and a lot of really weird concepts, but either way, hopefully that made some sense to you. But if not, as always, feel free to email me, reach out, chat with me so I can help clear up some confusion. All right, guys, that's it for the chapter, and that's it for this video. So I will see you in the next one. Bye.